Welcome to Lecture 18. We are now ready to begin Unit 5, where we are going to discuss the topic of rotation. So there are many things that rotate in our everyday lives. We've examined motion in terms of linear motion and the forces that cause motion and also linear momentum. But we have yet to talk about things that are spinning or rotating in some manner. So let's consider a spinning record. I want to ask you a question as you look at this picture here of a spinning record, and I want you to think about the points indicated on the record, point A here, point B, and point C. And as you're considering this record, it is spinning counterclockwise, so we'll indicate that as motion this direction. And of those 3 points, by the time they come back around, so they're going to spin around and come back to this point, and when they complete that one revolution, which of these 3 points, A, B, or C, has traveled the greatest number of meters? Or, you might want to think about it in terms of centimeters. Which one has traveled the farthest? Okay, if you're thinking about it, A traces out a small circle, 2 pi r around there. B traces out a slightly larger circle, and C traces out the largest circle, right? So if you were to take a tape measure and measure that distance that was traveled, you would conclude then that C has gone the greatest number of centimeters. Okay, but what about the amount of time taken to complete this revolution? What is true about points A, B, and C? Well, it should be self-evident that these 3 points are going to take the same amount of time to travel around one revolution, right? You can think about them as a spoke on a wheel, and as this thing rotates around and it comes back around, they will all reach this point again at the same time. So all the points take the same amount of time to travel. So what is going on here if they take the same amount of time to travel, but one of the points travels farther than the other 2? Well, if one of the points travels farther than the other 2, then distance divided by time would imply that the velocity of C is going to be greater than the velocity of B, which is going to be greater than the velocity of A. So, yet, even though how we traditionally measure velocity, distance divided by time, tells us different speeds, we also know that the angular speed, the speed with which the thing is rotating, must be the same if they all return to the same spot at the same time. So let's see if we can quantify these things a little bit better. If we think about the starting position of A, B, and C, and then later they are perhaps here, then they have traced out this line, and this line connecting them has traced out some angle which we can call delta theta. If I set theta equal to 0 here, then this is just some theta at a later point. And if we can describe theta as a function of time, then we can see what's going on with the angular velocity. So, first of all, before we do that, I want to define a convention that we use anytime we're talking about rotation, and that is that if the angle that's being traced out, the angular displacement, if you will, happens due to some counterclockwise rotation, then we assign that a positive sign. If the angle being traced out occurs by way of a clockwise rotation, then we give that a negative sign. So just so that we keep that convention in mind and we keep our signs straight. Okay, so it turns out then, if we think about what's happening as a function of time, you have some delta theta, some change of angle as a function of time, and that turns out to be sufficient to describe the angular velocity. That is, you can think about it as a time rate of change of angular position, d theta dt. And just the same convention applies to this angular velocity omega that applied to the change of angular position. If there's counterclockwise rotation, then omega is going to be greater than 0, and if there's clockwise rotation, it will be negative. There's going to also be the possibility of angular acceleration. Perhaps the record was speeding up or slowing down. And when that occurs, then we have some sort of acceleration, angular acceleration that is. And it might stand to reason that if the analog to position, right, so angular position, that time rate of change is going to be angular velocity, then it stands to reason that just the same way we had with linear velocity, remember that the linear velocity, the time rate of change of linear velocity was acceleration, so the same thing is going to be true with angular acceleration. We'll take that analog, angular velocity, and the time rate of change of it will be my angular acceleration. Okay, so these are completely analogous in the rotational picture to what we had in the linear picture so far. Okay, so like we did in the linear dynamics, we looked at a couple of position versus time graphs, velocity versus time graphs, and so on. Let's do the same thing in the rotational picture, and let's analyze a position versus time graph for rotation. So instead of linear position, now we've got angular position, which, by the way, in SI units, we use radians. So just be aware of that, it's not degrees. With this plot, we're seeing that the angular position starts off as -3 radians, and then as time goes on, it's changing angular positions. And so at what point can we deduce that the rotation is happening clockwise versus counterclockwise? Well, if there's a positive slope, then our convention tells us that that's counterclockwise. So at the beginning here we have counterclockwise as it's heading up this slope. Sometimes I abbreviate that like so. And then if we have a negative slope like we have over here, that's going to be clockwise rotation by our convention. Okay, and sometimes we abbreviate that as just CW. Are there any points where there's no rotation at all? Well, if the angular position is just staying the same over time, like here at the very beginning and here at the end, then there is no change of position, which means there's no rotation. Now, is there any acceleration involved? Well, this is a steady line, so just like we had in position versus time graphs in the linear picture, we would expect something not exactly linear if there was acceleration going on. So we don't have acceleration here or here. We do have a change of directions here, so that's tantamount to some sort of acceleration, but it's not a speeding up or slowing down, it's a changing of direction. Okay, what if we look at a similar graph now for velocity versus time? This time we're going to use angular velocity. What's happening now? So it's funny because these look like the same numbers, but they're not, because now we have radians per second on the y-axis. So it means something different. At the beginning here, where we have a steady -3, that means a -3 radians per second. So that's a steady velocity in the clockwise direction by our sign conventions. Here, however, it's becoming less and less negative all the way up to when it gets to 0. It's becoming less and less negative, meaning that the angular velocity in the clockwise direction must be slowing down. When it crosses 0, it has to be changing directions, right? Because now we're going to have positive angular velocity, which corresponds to counterclockwise rotation. Okay, and notice that it's becoming more and more positive, so it's getting faster and faster. It is speeding up in the counterclockwise direction. Then here what's happening, it's becoming less and less positive, so it is now slowing down, but it is still in the counterclockwise direction here, since we're still in the positive, and then at 0 we are remaining at rest. Okay, so I've given you some positive and negatives, but if we think about angular velocity and acceleration in terms of a vector, we can make some conclusions here as to how the vector is going to point. What we're going to use is something called the right-hand rule in order to determine this. Our convention, remember, is that counterclockwise corresponds to positive. When we have counterclockwise, such as in figure A, the rotation is like so, then you can imagine putting your fingers in that direction of your right hand, I should say, right, because this is a right-hand rule. Your fingers are going to curl around and your thumb will then point in the direction that the angular velocity vector is pointing in, which is in this figure up. Okay, that's also true in figure B. We have some counterclockwise rotation, our fingers point in that direction, and our thumb must be pointing up then. But the difference between figure A and figure B is that the angular acceleration vector is pointing in two different directions. In figure A, it's serving to work against that rotation and slow it down. So this is slow down, whereas figure B, we are speeding up because the angular acceleration vector and the angular velocity vector are pointing in the same direction. So it's just like we had in the linear picture, where it doesn't necessarily mean anything if the acceleration itself is quote-unquote negative or positive. It doesn't tell you whether something is speeding up or slowing down right off the bat. You have to also consider what's happening with the velocity vector. Okay, so what's going on with figure C and D? Well, this must be corresponding to clockwise rotation, where we are slowing down in figure C and speeding up in figure D. So be sure you understand why that is all the case. I would review that if it's at all unclear. Okay, so let's take and conclude everything that we have here. So we have another example of a wheel. If it is rotating clockwise and speeding up, how would you depict that acceleration vector? If it's going clockwise and slowing down, how would you depict that acceleration vector? So I would urge you to take a moment and make sure that you know how each of these acceleration vectors would point in these four scenarios, and go back to this image with the figures A, B, C, and D to see how that corresponds to the wheel and these four cases. Once you understand that, as I said, it's really analogous to the linear picture, and then we can move forward and make sure that we're understanding how to connect all of these things. All right, so speaking of the linear picture, remember that we had all of these equations of motion that described how an object would move given its velocity and acceleration and so on. Well, we have completely analogous equations in the angular picture. Instead of linear position, we replace that with angular position. Instead of linear velocity, we replace that with angular velocity. Instead of linear acceleration, we replace that with angular acceleration. And then the form of the equations is essentially identical. So these are completely analogous in that sense, and we're going to utilize them in the same way that we did in the linear picture. The only difference is in the linear picture we had to sometimes separate this out into x and y, whereas the rotational picture we really just need to think about whether the rotation is positive or negative. Okay, so is there a way to connect back to this question that I gave you in the first slide, where we talked about the fact that it seems weird that this record has is spinning at the same angular speed, but clearly has different linear speeds depending on where I am on the record. Well, we can derive a relationship to get between the linear picture and the angular picture if we carefully think about what's going on. So we talked about this being our angle theta. And let's say that the radius of my record is r, and the arc length that's been traced out by theta is s. There's a relationship that theta, in general, will equal the arc length divided by the radius. And so we can solve that relationship for the arc length, and we can say, well, this is the thing that's relevant when I was thinking about the linear velocity. I was thinking about 2 pi r being traced out, right? So the linear velocity was the time rate of change of s, right? So if I take that time rate of change of s and I substitute in this right-hand side of the equation, I see that I need to take a time rate of change of the product, r theta. Since it's a product, I need a product rule here where I've got two terms, the first term being theta dr dt plus r d theta dt. But the radius in general is not changing of the record, so that first term goes away, and I'm left with r times d theta dt. So this d theta dt we defined earlier as omega, and ds dt we've concluded is velocity, linear velocity. So I've derived a relationship that the linear velocity is proportional to the angular velocity, and the constant of proportionality is the radius of this record here. So now you see that when I plug in different radii, if I was at point A, I might have a different r than point B or C, and that explains why I have a different linear velocity while still having the same angular velocity. Okay, as for the acceleration, the linear acceleration, we already discussed centripetal acceleration before, being equal to v squared over r. We can also refer to that, by the way, as the radial acceleration. You can use either term synonymously. I can also replace this v squared with the relationship I just derived, that v equals r times omega, and I can re-express the centripetal acceleration in terms of omega. That is, that the centripetal acceleration equals r times omega squared. Then, so even if you are not speeding up, if the linear speed is remaining constant, you still have this radial or centripetal acceleration. But you might also be speeding up or slowing down with your linear velocity, in which case there will be tangential acceleration as well. So the tangential acceleration will be the time rate of change of your linear velocity. Again, replacing it with this relationship here, r omega, we can derive that tangential acceleration can be related to the angular acceleration by this equation here, where the tangential acceleration equals r times the angular acceleration. Okay, so what is the overall acceleration? If I had the case where I had both radial acceleration and tangential acceleration, then my overall acceleration will be the vector sum of these two, right, where it would be equal to the square root of ac squared plus at squared. Okay, but in many cases you may not have tangential acceleration. You may be moving at a constant speed and only have the centripetal or radial acceleration. Okay, so let's take an example. This is a little bit old school, but we're going to talk about a Blu-ray disc player. And with this Blu-ray disc player, we want to know how it operates in terms of coming to rest. The disc player has to be capable of taking this initial angular speed of 27.5 radians per second to rest in 2.1 seconds. And given that, we want to know, what does that amount to for the angular acceleration that the disc experiences? And how many rotations will it take for the disk to come to that rest? And then part C will also be what is the magnitude of the linear acceleration at point P, where you're at the edge of the disk. So we're going to utilize a lot of these equations of motion that we've just discussed, and we're going to try to deduce the answer to all three parts of this question. So let's look at part A first. Given the information that we have here, which is just the initial and final speed, right? We're initially at 27 radians per second and we want to bring it to rest. That means 0. And time. What can we use directly where we have all of the known information we have been given here and only the unknown quantity we wish to find? Which of these equations will allow us to do that? And so if you think about it for a minute, hopefully it's clear that that choice would be A. That doesn't mean that's the only way to solve this problem. Sometimes you can use one equation and then another, but in this case we may as well solve for it directly if we can. So when we apply this equation and plug in the numbers, we find an angular acceleration of negative 13 radians per second squared. It's good to see that we have a negative sign here. That makes sense since we are slowing down and the disk was initially moving in the positive direction. Okay, how many rotations will this amount to in this 2.1 seconds? Well, we know that a single rotation corresponds to 2 pi radians, and what we want to know is how many radians then is it turning through in the 2.1 seconds it experiences. Now this is not a constant speed with which it's going. Remember, it is slowing down. And so we want to find a way to account for that acceleration, or negative acceleration in this case. Based upon the choices here, C is the most sensible because we know the initial and final angular velocity, and we've just solved for the angular acceleration, so the only thing left to solve for is the change of angular position. Plugging in the numbers that were given to us, we can find that the Blu-ray disc then travels through an angular distance of, or displacement of, 28.9 radians. If we want to know what that amounts to in rotations, we've got to account for the fact that there are 2 pi radians in every rotation, and then we can conclude that that's a little over 4.5 rotations. Finally, for part C, we want to know about the linear acceleration experienced at point P at the edge of the disk. So for this, we need to account for the fact that there's centripetal acceleration, that component exists, and also, since the disk is slowing down with its angular speed, there's tangential acceleration too. So that my overall acceleration is going to be, as I said before, the applying essentially Pythagorean theorem and the square root of the centripetal acceleration squared plus the tangential acceleration squared, which we had these expressions for that we discussed, omega squared r being equal to the centripetal acceleration, and then r alpha being equal to the tangential acceleration. And if you simplify this expression here, you see that it corresponds to choice E. So, by the way, what is the direction of that tangential acceleration? If this was initially moving in this direction, then the tangential acceleration would be A. If it had initially been moving this direction, then the tangential acceleration would be B. C points in the direction of the centripetal acceleration instead. So then the last step is just to compute each of these components. First of all, the radial acceleration, or the centripetal acceleration, turns out to be equal to this. The tangential acceleration turns out to be equal to that. The negative sign is due to the fact that it is slowing down. But of course, when we put it into the Pythagorean theorem, that'll get squared, the negative sign will go away, and we will find a total linear acceleration of 1.8 meters per second squared. Okay, next time we will do some more examples, but I hope this has given you a good introduction to rotation.